Yesterday we learned that a system of equations is where we have more than one equation with more than one variable, and we're trying to find out what makes all of them true. Okay, so yesterday we were working with two equations and two variables. We graphed them out to find our solution. Graphing has a lot of limitations because it can be difficult to graph. Then once we get a graph, even if we're really careful, we still have to confirm that we found the right solution by plugging it in, because if our graph is just slightly off, we can be picking the wrong point. Also, there's no way we would ever be able to find a solution that has fractions or decimals in it by graphing, because we just would not be able to pick the right fraction or decimal from out of a grid in a graph paper. So there's kind of some pros and cons there. It's nice that with solving by graphing, it's building off of something we've done before. We've already learned how to graph lines, so it's building off of some common knowledge, but it has a lot of limitations in terms of actually being able to find the solution. So we're going to learn two algebraic ways to solve systems of equations. We're going to learn one today and one tomorrow. You may remember these from Algebra 1 once we get going. Students usually have a preference on which method they like better, and most students prefer the method that we're going to learn tomorrow. But I'm going to ask that you do it the way we're learning today, even if you happen to remember that other way, so that we practice both ways. The way we're going to learn today is called substitution. And what substitution does is it gets one variable all alone by itself in one of the equations, and then we substitute or plug in what that variable is equal to into the second equation. That means there will only be one variable left, so we can solve for that variable, and we're going to take that back to the original and plug it in to get our second answer. So to solve by substitution, our first step is get one of the variables and one of the equations all by itself. It doesn't matter which one, but sometimes there's an easier one. An easier thing to get alone will be one that doesn't have a coefficient. Because if it has a coefficient, we're going to have to do some dividing. So in this problem, the x in the second equation is the easiest thing to get all by itself. I can do that by subtracting 2y from both sides in that second equation, and that leaves x is equal to 2 minus 2y. So our first step is to get one of the variables and one of the equations all by itself. It could be any of them, but the easiest thing will be something that doesn't have a number in front of it. Then what we're going to do is say if x is equal to 2 minus 2y, that means x is exactly the same as 2 minus 2y, and I can take that and substitute it or plug it into x in the first equation. So that first equation is going to become 3 times, instead of x, 2 minus 2y plus 4y equals negative 4. So we use the equation that we haven't used yet and replace the letter that we got all alone with what we found that it is. Then you should only have one letter left, so now we can solve this equation as normal. We're going to distribute the 3. Combine our like terms. Subtract 6 from both sides. And divide by negative 2. And that gives us our first solution, but we are more than halfway done with the problem. It's not as much work to get the second solution. So our steps on the previous one said get one of the variables and one of the equations alone. So we got that x alone. Then the second thing that it said to do was plug it in or substitute it into the other equation. And then the third thing it said to do was solve for whatever letter is left. So we've done that. There's only one more step, and that's to find out what the other letter is. And we do that by taking this answer and substituting it or plugging it into where we had gotten the other letter all by itself. So x is equal to 2 minus 2 times y, and we just found y is 5. So x is equal to 2 minus 10, or x is equal to negative 8. We're going to give our answers as ordered pairs like we did yesterday, because this problem is doing the same thing as the problems did yesterday, it's just using a different method. Yesterday we were looking at a graph, today we're just looking at the algebra, but it's still doing the same thing. It's finding the point that works in both of these equations, so we're going to represent our answer as a point, x, comma, y. Questions? Get one of the variables in one of the equations alone, plug that into the other equation, and solve for the letter that's left. Then take that answer and plug it into your second answer. Okay, what one is going to be easiest to get alone here? The top y. It still kind of has something in front of it. We need to be careful that it does actually have that negative in front of it. So that equation is 3x minus y equals 13. If I want to get that y alone, what do I need to do? Subtract 3x from both sides. That gets me negative y is equal to 13 minus 3x. I'm not done yet because I want to get y alone, and it is not totally alone yet. What do I need to do? Divide everything by a negative 1. That gets me y is equal to negative 13 plus 3x. So that's step 1. Pick one of the letters in one of the equations and get it by itself. Then we take what we found and plug it in or substitute it into the equation that we haven't used yet. So we rewrite that equation as 2x plus 2 instead of y, what we found y is, which is negative 13 plus 3x equals negative 10. Then we solve as normal from here, distribute. Combine like terms. Add 26. And divide to find that x is 2. That's our first answer, but it's our third step of the problem. We literally have one more step to do, and that's to take that x is equal to 2 and substitute it or plug it back in to where we had solved for our one letter already. So y is equal to negative 13 plus 3 times 2. Negative 13 plus 6 is negative 7. Yeah.
After you did the distributive property, where
Yep.
that two, is it just,
When I distributed it, I multiplied that 2 by the 13 and the 3, so it became a 26 and a 6.
so it doesn't say that?
No, because I multiplied it. That's what the distributive property is doing, is multiplying it by the stuff inside. So the 2 and the 13 combine together to make the 26, and then the 2 and the 3 combine together to make the 6.
Does it matter, like, which equation you pick at the very beginning?
It doesn't. So you can get any of the 4 letters by themselves. It doesn't matter which one. So I always go for whatever one looks like it's going to be easiest. And if there's more than one that's all by yourself, it doesn't matter. You just pick one of the letters. Or if there's nothing that's all by yourself, you just pick one of the letters. But if there's only one letter that's by itself, that's the one I go for, just because it's easiest, but it doesn't actually matter. We're going to write our final answer to this problem as 2, -7, x comma y. Questions? What should I go for here? The negative x. So to get that negative x alone, I would start by subtracting 3y from both sides of the first equation. Which will leave me negative x is equal to 1 minus 3y. It's not totally alone yet. Still has that negative. So I need to divide everything by a -1, or you can multiply everything by a -1. That's the same thing. I get x equals -1 plus 3y. So that's our first step. Pick one of the letters in one of the equations and get it alone. Then I'm going to take what I got for that and plug it in or substitute it into the equation I haven't used yet. So I'm going to rewrite that equation. 4 times, instead of x, -1 plus 3y plus 6y equals 8. I'm going to distribute, and I get -4 plus 12y. Combine like terms. Put together the y's to make 18y. Add 4 to both sides. And get 18y is 12. And then I would divide both sides by 18, which gives me y is equal to reduce. They don't both reduce by 6, so that gives me 2/3. Don't give me this as a decimal because it's 0.66666, so you're going to have to round that off some point. So fractions are better answers. Okay, give them as reduced fractions is how you should give your answers. Once we find what one answer is, we take that answer back and plug it in to find our second answer. -1 plus 3 times, we just solve for y is 2/3. 3 times 2/3 is 2. So I get x is 1. So our answer to this one is 1, 2/3. This is a problem we could not have solved by graphing. With having a fraction answer, that would be something we would not be able to see on a graph. So fraction answers in your homework are not wrong answers. A lot of times when students get fractions, they start to worry that that means that they've done something wrong. Fractions are not bad numbers. They are just numbers. Okay, so don't be afraid of getting fractions for answers. We cannot get fractions for answers when we're solving by graphing, because then we would just have to estimate them and that would take forever. But we can get fractions for our answers when we're solving algebraically. So don't be surprised if you do get some fractions for answers. Questions?
What if you could like what if I don't like 0, like the x's cancel out?
We will talk about that in a little bit. So it says here, if you solve and get a statement that is absolutely always true, so something like x equals x, 4 equals 4, 0 equals 0, then the two equations are actually the exact same equation, and that means there are infinitely many solutions. What did that look like when we graphed them? Same line, okay? So if we end up with something that in geometry we call reflexive, or an identity statement that is absolutely always true, something equals itself, that means there are going to be infinitely many solutions. Like graphically, they're actually the same line. If you solve and you get a statement that is absolutely and always untrue, something like 7 equals 6, then the two equations are actually parallel when we graph them, and there is no solution for that. Okay? This does not account for x equals 0. Okay? Sometimes students will get an answer of x equals 0 and assume that that actually falls into one of these two categories. X equals 0 is not this. X equals 0 is an answer. Okay, 0 is a number and it's a good number. Okay, but if you get something that is absolutely always true, like 0 equals 0, or something that is always false, like 0 equals 4, then we have one of these two special situations. So in this one, what would be easiest to get alone?
X.
The first x. So I would do that by adding 2y to both sides in that first equation, and that gives me x is equal to 3 plus 2y. I'm going to take that and plug it in for x in the second equation. That gives me 2 times 3 plus 2y, substituting in the x, minus 4y equals 7. When I distribute, I get 6 plus 4y minus 4y is 7. When I combine my like terms, 4y minus 4y is no y's, so I end up with 6 equals 7.
No solution.
That's a little bit of a problem because 6 does not equal 7. So there's no solution to this problem. That means if we would graph these two lines that they are actually parallel to each other. There's no point that is going to make both of the equations true.
So we would just stop.
So we just stop. Yep. Yep. If you end up with something false, you just stop there and say there's no solution. Questions? For this one, what would I get alone? The first y, so I would do that by subtracting 2x. I get y equals 5 minus 2x. I take that and I substitute it or plug it in for y in the second equation, which gives me 6x plus 3 times 5 minus 2x equals 15. Distribute. Combine like terms, 6x and 6x makes no x's, so I'm left with 15 equals 15. 15 always equals 15 for sure, forever. So that means that there are infinitely many solutions. They are actually graphically the exact same line. Questions?
So if something 0, 0 is infinite many.
0 equals 0 being infinitely many.